Hello, good morning. Can you hear me? Hello? Hello, can you hear me?
Yes, sir.
Okay, right. Let's start today's lesson. So last time we were talking about division algorithm. We learned in last week, we learned about a different version of division algorithm. It is a slight variation of original division algorithm. We know that division algorithm means if b is any integer and also the a is a positive integer, then b is equal to a q plus r, right? So r is 0 up to r can be taken integer values 0 up to b minus 1. Now, in last time we were discuss about that slight variation of that. Then according to that, we can allow to take negative numbers for the r. So then, I mean, the symmetrically to the original one, we did that, right? Okay, now today we are talking about greatest common divisor. I think you can see my writings, right? Greatest common divisor. Okay, so let's start with this notation and this question. So usually we use this notation to represent greatest common divisor of two numbers. Let's say 75 and 30. Can someone put the answer to the chat box? GCD of 75 and 30, what is it? I think you are familiar with this from grade 4. Yes, see, let's see. Yeah. The 15 is the answer, right? Now let's start this one. GCD 13, 21. What is this? This is the answer is 15. And what is this? 1. Yes, it is 1, right? So okay, now I can ask a different one. GCD, sorry. GCD, let's say 2 to the power 7, 5 to the power 3, 11, 2 to the power 5, 5 to the power 2 to the power 5, 5 to the power 7, say 13. So I represented it as both numbers as its product of prime powers, right? Now, what is GCD, right? And when typing the power in usual typing way, you know that for example, to represent 2 to the power 3, you can use this notation. Usually we use that notation. You can write it as that in the chat box. You can put the answer. Or 3 to the power 9. We can write it as, we use this notation to represent the power. Right. So let's see the answer. You can put the answers. 2 to the power 5, 5 to the power 3. Yes. 2 to the power 5. Yes, that is 2 to the power 5, 5 to the power 3. In a sense that greatest common divisor means actually definition is in the name, right? Greatest common divisor. That means the highest common factor, of course. Greatest common divisor mean highest common factor, right? So, of course, you can identify from these two. The highest common factor means the largest factor which divides both numbers. The largest factor which divides both numbers. That is, of course, 2 to the power 5, 5 to the power 3, right? That is the largest common factor which divides the both integers. So, so you know very well the meaning of greatest common divisor, right? Okay, but here now I already actually posted today's note. However, I'm writing the definition again, that definition. Greatest common factor. Let's say GCD, right? So we are giving now a new definition. Perhaps you are not familiar with this definition. So we, from our school days, we identify greatest common divisor as the largest number which divides the both integers. Or if we're talking about the greatest common divisor for 3 numbers, the largest number which divides both integers, all integers, for say 3, right? Now, here, this is the same, this definition is agree with that, but here we give some strange definition. Strange mean, in a sense, it is not simple compared with, because you know that it is not a difficult definition for GCD, right? Greatest common divisor is not a difficult definition. We can, I mean, if someone explain it to us, we can easily understand. But here we are using some strange definition, that is, let A and B, you are not, this is available, right? I'm writing it with some minimal words. So let A and B integers, right? With at least one of them different from zero, right? So then GCD-AB is the positive integer D satisfying, yeah, now you can see satisfying two properties. What are those two properties? First one, D divides A and D divides B. From the first condition, it says that first of all, greatest common divisor must be a divisor of both integers. I think you agree with me, right? And the second condition, this is the second condition. If some integer C divide A and C divide B, then C less than or equal D. Okay. Now, from the second condition, what you feel? From the second condition, you can see from the first condition, that greatest common divisor must be a divisor, first of all, right? From the second condition, we give the property that divisor must be the largest divisor among all divisors of A and B, right? That is why it says if C divide A and C divides B. What does that mean? If C is any divisor of A and B, then C is less than or equal to D. From the second one, we give in that largest property to the GCD, right? From the first one we give in the property that GCD must be a divisor, and from the second one, we give the property of the largest divisor, right? So in that sense, though we present it in this somewhat complicated way, you can see again it is we can easily understand that definition also. Now, so there are some several importance in this definition. Of course, when we proving something, when we proving the statements, or when we state some theorems about greatest common divisor, and if we want to prove that theorem, then we need the proper definition. We use this definition. That is why we need this definition. This is the standard definition of greatest common divisor in the field of number theory, right? So in your school days, you just understand that you understand about the greatest common divisor only, I mean, without any proper definition, just the, of course, the definition is clear, but we don't give this kind of definition in your school days, right? Now, example. So let's see this example. Find the greatest common divisor of minus 12 and 30. Put your answer to the chat box. And also, that is the first one, and the second one is GCD of minus 30 minus 12. Put your answer to the chat box, to both questions. Yeah, some says 1 6, right? Some 6, yeah, some says 6 6. Yeah, the answer is for the both one, it is 6. Why? So here of course, that what are the common divisors for the minus 12 and 30, right? The minus ones also common divisors. For example, that minus 1, minus 6, minus 2, minus 3, and so on. This and also 1, 6, 2, 3, right? Those are common divisors of this one. Also the 4, right? 4, minus 4, 4. Those are the common divisors. And again, what are the common divisor for the 30? Minus 1, 1, minus 3, 3, minus 5, 5, minus 6, 6, minus 15, 15. Of course, the 12 and minus 12 are also the divisor of minus 12, right? And minus 30, 30. Now, among those divisors, the 6 is the largest device, right? It is very easy to then it is very easy to find that the greatest common divisor of minus 12 and 30 is 6. And for the second one, minus 30, minus 12. Of course, again, the positive, this is the fact, the divisors of minus 12 are the same, and the minus 30 also get the same divisors as 30, right? If you put the negative sign, we don't get any different divisors. It has the same divisors as the positive number. So again, the greatest one is 6. So in both cases, it is 6. Okay, let's see which is one. GCD 0, 5. 0, 5. GCD 0, 5. What is the greatest common divisor of these numbers? Yeah, it is 5. Okay, what about this one? GCD minus 1, minus 1. GCD minus 1, minus 1. It is 1, right? So, okay. Now let's move into the. So that is the definition. Okay, what about this one? I can ask this. GCD, I can ask this question. GCD, say A is an integer. What is the greatest common divisor of these two numbers? Let's see an answer. Okay. Some says A. Is that right? Compare with minus 1, minus 1. Right? Be careful. Is the answer A? Yeah, I think that someone write the correct answer. It is not A, because in that sense, GCD minus 1 must be minus 1, but it is not. It is plus 1, right? So, so this is equal to modulus A. That means if it is negative, the positive one is the greatest common divisor, right? If you need any clarification, please ask. If it is not clear, if it is not convincing, you can ask the question, right? By talking to me or by putting the question into the chat box. Okay. Right. Okay, what is GCD AN minus 2A? What is this then? put the answer to the chat box again. Okay, let's wait for further answers. Okay, I'm waiting for more feedbacks. Okay. Yeah. Right. Yeah. The answer is mod day. Right. Someone write it like that way. The plus A. Don't do that, because what is that mean? Actually, even A is equal to -2. This means plus -2. That means it is equal to -2. Right. The proper way to, I think, yeah, perhaps that for that answer plus A, he implied he wanted to write it like that positive of, or the positive value of A. But if you write it in this way, it is incorrect. That to write the positive value of A, irrespective of its sign, you must write it like that. Actually, you know that, right? Mod A equal to minus mod A mod also, right? Okay. Right. Now, this is the, now you can actually, from this theorem, you can understand the importance of earlier definition. So I'm giving a theorem. This is a very, very, very important and very, very useful theorem about the greatest common divisor. Perhaps you don't know about this theorem earlier in your sorry. This is the theorem, THEOREM. See this theorem. Given integers A and B, this theorem include in your note also, integers A and B, not both of which are 0 there exist integers X and Y such that GCD AB equal AX plus BY. Right? Remember that X and Y are integers. What does that mean? Actually, that means you can represent greatest common divisor of two elements as a linear combination of that elements A and B, right? The coefficient is taken from the integers. For example, we know that GCD 5 and 7 is equal to 1. So that means definitely we can find two integers according to this theorem. We can find two integers such that 5x plus 7y is equal to 1. Now just find the x and y. Find x and y for this case. According to that, that theorem, this makes sure that we can find two integers x and y which satisfy this equation. Try to find x and y and put the answer to the chat box. 5x plus 7y is equal 1. Remember that you need to find integers x and y such that if you put those integers into this equation, satisfy the equation. Yes. So I get a 1. Yeah, correct answer. Now you are writing it. X equal minus 4. Y is equal 3. X equal minus 4. Y is equal to 3. Let's ask this one. GCD. Find xy. Find xy such that GCD say 6 yeah 12 4 12 4 oh, no 12 8 is equal to 12x plus 8y. Right? Again, according to that theorem, it is make sure that such integers exist. So find that integers x and y. Yes. Some noises coming. Please off your microphone. Right, any answer? Yeah. X equal 1, y equal minus 1 for that case, right? For that case, x equal 1, y is equal minus 1. But what about this, this kind of problems? We know that GCD 200 and say take a prime number. Is that 97 prime number? Yes. Then definitely that GCD is equal to 1, right? Because 97 is a prime number, right? Then according to that theorem, again, we can find two integers x and y such that which satisfy this equation. But remember that you can see it is very difficult to find such integer x and y. But according to the theorem, it is exists. The theorem do not facilitate how to find those integers. Later, we will learn some algorithm called Euclidean algorithm to find those integers x and y, right? So we will learn it later, right? Euclidean algorithm. So though that theorem state that there are two integers x and y which satisfy that GCD AB is equal to x plus by, it doesn't give any method to find those integers. Theorem only state that exist. We call that existence proof, right? So now we are going to prove the theorem, the proof of the theorem, right? Can you remember the well ordering principle? So can you remember that in that beginning of that lesson, the well ordering principle, I mentioned you that it is a very important principle, and we are using that principle to prove several future theorems. This is again one of that. Right? What is well ordering principle? Of course, well ordering principles means if A is a subset of non-negative integers, or A is a subset of natural numbers, right? And A not equal empty, it is very important. If A is a non-empty subset of natural numbers, then least element exists. Least element of A exists. Of course, that's a unique integer, unique natural number, then the least element of A exists. That is the well ordering principle, right? Now we are using actually that principle to prove the existence of that integers X and Y, right? So we want to prove the existence of, so this is the existence of XY such that GCD-AB, whatever value for the GCD, these two integers X and Y exist, right? So to use the well ordering principle, first we need to define the set S. S is equal to AU plus BV, AU plus BV greater than 0 UV integers. Of course, we are going to prove this claim. We are proving, we are going to prove. You don't need to write these things in the proof, right? I mean, you can see the proper proof in the note. Here I am facilitating you to understand the theorem. We are going to prove the least element of S is the GCD of AB. You can see that first of all, we need to prove S is non-empty, of course, right? First, we prove S is non-empty. If we prove S non-empty, then trivially that least element exists in this form, AU plus BV, right? This form it is exist, and then actually we are going to prove that is the greatest common divisor of AB. If we prove that thing, then that means GCD-AB is in this form, AU plus BV. We can write it in AU plus BV form, right? The proof complete. So first of all, let's prove S is non-empty. What is the best way to prove S is non-empty? So you can use several methods, but easier way is substitute U equal A and B equal V. Then AU plus BV is equal to A squared plus B squared. Can it be 0? No, because actually in the theorem we just says okay, so do you have the, yeah, given integers A and B not both 0, right? So this must be greater than 0 because AB not both 0. again, that means at least one element is non-zero, right? So a squared plus b squared greater than 0. Therefore, S non-empty because S is non-empty, right? Because the a squared b squared is a member of S. A is non-empty. Therefore, the least element. So you don't need to write this. The in the note you can see the proper writing in there. So I'm just writing the steps here to understand you, right? To explain the proof to you. So therefore, least element of S exists. Of S exist, right? Let it be of course you can take it as you don't need to, if you confusing with the, usually we use, okay, let it be D, right? Remember that D is not the greatest common divisor. It is the least only element of S. This is D equal least element of S, right? Now the point is we are going to prove now we are going to prove D is nothing but GCDAB. Is nothing but GCDAB. How we prove that? Recall the division algorithm. According to the division algorithm, according to the division algorithm, we know that so A is equal to, because D is greater than 0, right? D is greater than 0. So A is equal to QD plus R, right? And what is R? R is in between 0 and D. It is strictly less than D. Or someone can write R is less than or equal to D minus 1 and greater than or equal to 0, right? We know that D is greater than 0 because it is the least element of S, right? It is greater than 0. Why it is least element of S? We show that S is non-empty and all the element of S is positive, right? S is, all the element of S is positive because AU plus B positive integers, AU plus BV equal greater than 0. So we use the division algorithm, right? So it is in between D minus 0 and D minus 1, right? R is less than or equal to. Now use this trick. Therefore, A minus QD equal, right? A minus Q AX plus BY, X plus BY, which is equal to A1 minus QX plus B minus QY. Now let's focus to that one very carefully. Why I am writing it in this case? D, yeah, I can explain it. D is an element of S. Therefore, there exists. So you can see that the nature of the element of S, what's those look like? It is look like AU plus BV. It is consist of all elements such that AU plus BV and its value must be greater than 0. So UV integers, right? So that D is least element of that one. So that means D is already an element of S. So there is some X and Y such that D is equal to AX plus BY, right? D belongs to there exists XY. D is an element of X. Is there exists XY such that D equal AX plus BY, right? That is why I write down this step, right? Now it is equal to A 1 minus QX, B minus QY, right? Now, actually, we are going to prove R is equal to 0 first, right? Now, if R greater than 0, then what happens? Then R is element of S. Can you see it? Because A minus QD means R, right? So this is R. R is equal to A minus QD. See this argument carefully. A minus QD. R is equal to A minus QD, and we write it as A 1 minus QX, B minus QY. It is on the form A U plus B V, right? If R is greater than 0, you can see carefully, then AU plus BV is an element of, we know that R greater than 0, AU plus BV greater than 0, right? That's mean AU plus BV is element of S. That means, you can put U naught and VV naught to distinguish it from general UV. So R is an element of S, right? But this contradict with what? But this contradict with R is the, D is the least element of S. Can you see? D is the least element of S according to our assumption, right? We put D's. We consider D the least element of the set S, right? So, but we know that from division algorithm, this is true. R is in between 0 and D. Now, if the R is not equal to 0, that means R greater than 0. So, also R can be write in this form. That means it's contradicts. That means R is in S. So it contradicts with D is the least element of S. Therefore, R cannot be 0. R cannot be greater than 0. Therefore, R must be 0. Right? So therefore, D is a factor of, or divisor of A. Can you see it? So here, A is DQ plus R. If R is, so we proved that R is equal to 0. So what is that mean? A equal QD, right? That means D is a divisor of, or in other words, D divides A. So D is a divisor of A. Similarly, the same argument, D is a divisor of B also. D is a divisor of B, right? So D is a divisor of B, and And now D is a common divisor. Therefore, the similar arguments, right? Here the similar arguments, by similar argument, D is a divisor of B. Therefore, D is a common divisor of A and B. So which satisfy that first condition of the greatest common divisor, right? First of all, D is a common divisor of A and B. So we already proved that least element of that set is a common divisor of A and B. We proved that. Now we want to show that is the largest one, right? How we prove that one? Now let's see CB and arbitrary common, say positive divisor. It doesn't matter, right? Because negative divisors always less than or equal to D. So it is enough to consider CB an arbitrary positive divisor of A and B. Of A and B. You don't need to write this proof because I am writing this only for explain the proof to you. I'm not writing it properly. The proper proof is in the note, right? So arbitrary positive divisor on A, therefore C divide A and C divide B, right? Therefore, C divide, we know that if C divides A and C divides B, C divides AX plus BY, right? C divide AX plus BY. What is A? Now X is the element, Y is the element which satisfy this now. D equal to AX plus, those are fixed elements, right? Which satisfy that. That means C divide D. Therefore, C less than or equal D, right? Can you see the argument? C is a positive divisor. Now C divides AX plus BY, right? If some positive divisor divides another positive divisor, that means it is always less than or equal to that dividend, right? So so it is less than or equal to D. Therefore, this is the second condition of Y, actually the 1. So what is 1? D is a common divisor of A and B. From 1 to GCDAB equal to D. So we prove the theorem, right? So please understand the proof carefully. Try to understand it in the complete proof is in the notes, right? Now I already explained the proof to you, and patiently read the proof later in the note and see that whether you can understand the proof, right? Okay, some questions about the, sir, can we say if a common divisor exists in set S, there should be a greatest common divisor in set S by completeness? Sir, can we say if a common divisor exists in set S, there should be a greatest common divisor in set S by completeness? Yes, we can say like that. If a common divisor exists in set S, there should be a greatest common divisor. That means also that common divisor can be a greatest divisor also. For example, remember that C is less than or equal to D, right? So if a common divisor exists, there should be a greatest common divisor in set S. And yeah, this is not true for the this one, right? At least AB doesn't equal to 0. At least 1 is not equal to 0. That is true. But for this one, you can see if for example, for this set, if we take S as AU plus BV, 0U plus 0V. I mean, if A equal 0, B equals 0, then of course it has a common divisor, like 1 is a common divisor, but the greatest common divisor doesn't exist, right? With that condition, I mean at least one of A and B done 0, then we can state that one, right? Are there any questions? Okay, so now time is 7:55. I am giving you a 15 minutes break. Please log into the same link on 7:10, and I need another 20 or 30 minutes to complete the today's lesson, right? So let's meet around let's meet again around 8:10. Now 7:56, 8:10, and so I'm taking 20 or 30 minutes for complete the rest of the lesson. And again, if you want, you can ask any question after that period. Right. Okay. So please come back around 7:10, 8:10. Okay, let's come back to the lesson again. Let's share the screen again. Right. Actually, the last question in the chat box, it's a good question. I want to give more comments in that question. So before jumping to the next item, I will give more comments on that question. Of course, if you take any two integers, A, B integers, right? Let A be any integers, right? What about the divisor? Is that common divisor exists for any A, B belongs to Z, or any A, B in Z? The common divisor exists. A common divisor, Yes, that's right. Yes. So can you name one? Just a common divisor if A, B belongs to Z. What is it? I mean, yes, one actually. Also we can say -1, right? For any A, B belongs to Z, at least two different common divisors exist. What are those? 1 and -1, right? Now the next question is now, so we know that if you choose any two integers, at least, we know the actually the two common, at least two different common devices exist. Now what is the limit? I mean if you choose any AB belongs to shade, or is there any, are there any AB in shade such that common devices, number of common devices are infinite? Now, my next question is, are there any AB integers such that number of common devices of those two are infinite? What is the answer? Number of common devices are infinite. Yes, very good. The 0, 0 is the only answer. You can see that from this exceptional case, for the 0, 0, you can find infinitely many common devices, because if you choose any integer, that is a common divisor of 0, 0, right? Now the problem is, if at least one is non-zero, if we choose at least one is non-zero, what about number of common devices? A not equal 0 or B not equal 0. Number of common devices always finite, right? Number of common devices always finite. Right? So it is a number of common devices A. What does that mean? You mean A means that the number A. What do you mean? No. If B is 0, yeah. Of course, not A, right? Because you can take the minus values also, right? So perhaps you can say the number of positive common devices. I mean, if A is A, right? Make sense? Because the minus 1, 1, yeah, right. So if A, B are any integers, at least one of them is non-zero. Number of common devices is finite. Now, if you choose any finite set of integers, always maximal element exists as well as the minimal element exists, right? So, so then we have a guarantee that the greatest common divisor exists in that kind of sets, right? Because the number of elements is always finite, because we are talking about the greatest common divisor only for the two elements, at least one of them is non-zero, right? I just wanted to comment it on more, right? Okay, now let's move into that. I think if you want to ask it about more, you can ask after this session also, right? You have a chance to ask. Okay, now yeah. This definition is very common. AB is said to be, you already know this, I think, relatively prime, not prime, remember that, relatively prime, if GCD AB equal 1, right? Okay, just answer this question. Find a relatively prime element. Element for 10. Relatively prime element for 10. Just put your answer into the chat box. Yes, 1 is relatively prime. More answers different from that. There are plenty of answers, right? 1, 3, 5, 7, 9. Okay, yeah, and so on, right? So you can see that 2 is not relatively prime to 10, and -2 not relatively prime. Also 5 is not relatively prime. -5 is not relatively prime. Also the 15 is not relatively prime, right? Any even number is not relatively prime to 10, and so on. So I think you got the idea. Okay, now okay, let's again let's move into a theorem again. What is that? Again, a very important theorem. Let A and B integers not both 0. Then A and B are relatively prime if and only if, I use the notation, if and only if there exist x and y such that ax plus by is equal to 1. Right? So this is interesting because of this if and only if word, or the otherwise you can see that for the one way it is very trivial according to the definition of or according to the earlier theorem, right? Suppose, now proof, suppose AB relatively prime. Therefore, GCD AB equal 1. Therefore, by earlier theorem, we can directly say that theorem there exists x and y such that ax plus by is equal to 1. Actually, nothing to prove there, right? I mean that. It's a direct application of earlier theorem. Now suppose, it is a if and only if statement. Now suppose Ax, there exists the other way. There exists x and y in shape such that Ax plus by is equal to 1. Now then we want to show the GCD is equal to 1, right? Now let GCD AB equal D. Therefore, D is a common divisor of A and B. D divide A and D divide B, right? Therefore, D divide, you know that from that property D Ax plus by. Therefore, because Ax plus by is equal to 1, D divide what? Right? But D is positive. We know that D is positive integer because greatest common divisor is positive. Therefore, only positive integer divides 1 is 1. right? Therefore, D is equal to 1. So we prove the both way, right? If you want more clarification, you can ask after this session. I want to finish it quickly. This is another theorem, very important theorem again. If A divides C and B divides C with GCD AB equal 1, then AB divides C. Okay, now my question is this condition necessary? Which condition? Is this condition necessary? Is this necessary? Before proving this theorem, I want to make sure whether that condition is necessary. That means if it is not necessary, you can give a count example. I mean, if it is necessary, you must give a count example such that A divides C and B divides C, but AB doesn't divide C. I mean, if we remove that condition, can you remove that condition? Actually, I'm waiting for your answers. Can you give counter example to show the necessity of that condition? Necessity of that condition. So give a count example. If we remove, I mean, without that additional condition GCDAB equal 1, this statement is false. Can you find a count example in such a way? Yes. Let's see, one answer already came. B equal A. So it is not a particular case, but let's see whether it is true. B equal A. Then B is equal A. But the thing is, unless I mean the A must not be equal to 1 then, right? In that case, because if it is 1, then GCDAB is equal to 1 if 1 is equal to 1, right? Of course, B equal A, and it is not equal to 1. Then of course, and O minus 1, right? 1 O minus 1. Then GCD AB is equal to mod A, right? And which is not equal to 1. So then it is violating that condition, right? But again, see, this one AB, right? AB, here it says divide C. Yes. So what is your C then? You must say what is C, right? So I think you mean what is your C? Hello, that so yes, B equal A. So answer is not complete unless you give a value to C. What is your C? C is not 1 no 0. Yeah, but I think it is, we cannot, I mean, for some C's, then again, this statement true. Yeah, better try to find a concrete numerical example. So I will give one, right? So this one, take A as, say, of course, A is equal to 4 and B is equal to 6 and C is equal to 12. See, now 4 divide 12 and 6 divide 12. But 4, 6, that means 24 does not divide 12. That's an example, concrete example for show that the necessity of that condition, right? Without that condition, we can find some values for A, B, C, which fails this statement. Okay, now let's prove the theorem. So the proof of the theorem, A divides C and B divides C. Therefore, there exists R and S such that A C equal AR equal BS. C equal AR and C equal BS, right? But also the GCD AB equal 1, right? Therefore, there exists X and Y such that AX plus BY equal 1, right? Now, C equal C times 1, which is equal to C times AX plus BY, which is equal to ACX plus BCY, right? Now, remember that ACX plus BCY, now you can put C equal AR and C is equal to AR and C equal to BS. So BS. Sorry. Put there. Okay. Put there BS. A B SX plus B A BAR Y, right? So you can take AB out then. AB SX plus RY. What does that mean? Now C is equal to AB SX plus RY. This is an integer. According to our definition of divisibility, therefore, C divides AB. right? Now, remember that we use this additional condition because A be relatively prime in the proof, right? Without that condition, we cannot prove that one. So the proof complete, right? So it's a very important theorem. Again, this is another similar one, but it is little bit difference with the earlier one. GCD AB equal 1. Then AB divides C. No. So other way. Sorry, it's the earlier one. It is similar to the same one. A divide BC. Okay, so I want to erase that. This is called Euclid's lemma. Right? Euclid's lemma. If this is the Euclid's lemma, if A divide BC with GCD AB equal 1, then A divides C. If A divide BC with GCD AB equal 1, then A divides C. Right. Again, my question is, can we remove this condition? Actually, that condition is necessary. Now, if so, can you find a count example to show the necessity of that condition? That means find some values A, B, C, which violating this condition, and show in that case, this is not true. Now try a count example. You need to find A, B, C such that which violating this one, that means in that case GCDAB doesn't equal to 1, and also in that case A doesn't divide C. Of course, you can find some integers which violating that condition, GCDAB is equal to 1. But still it satisfies this one. I'm asking for a okay, one asks equal 3, B equals 6, C equals 7. Yeah, let's try this one. A equal 3, B equals 6, C equal 7. You can see that then GCDAB doesn't equal 1, right? But let's see whether it satisfies the other condition. Then A divides, A means A divides BC. Yeah, so what is BC? It is equal to 42. 3 divides 42. That condition is correct, right? Now, what about that one? A divides C. A is equal to 3. C is equal to what is C? C is equal to 7. That is incorrect. Right? So yeah, that's an example for violating that. I mean, the example for to show the necessity of GCD AB equal 1. Right? Good. Okay. So now let's prove the theorem again. The Euclid's lemma. It's a very easy proof since it is easier than the earlier one. Actually, AB equal 1. There exists xy such that ax plus by is equal to 1, right? Therefore, if we multiply both by c is equal to acx plus bcy, right? But we know that, but a divide bc and a divide ac. Why a divide bc? Because of the condition of the theorem given, right? Because of that, therefore a divide acx plus bcy, but acx bcy, but what is that? acx bcy is equal to c, therefore a divide c. The proof complete. Right? Now you can use this theorem to I mean, you can apply those things. Now, for example, this is an example. I will explain it very quickly. Show that the numbers. This is not the application of Euclid lemma or the earlier one, but application of, can you remember that theorem that if GCDAB is equal to 1, if and only if there exists xy such that ax plus by equal to 1, right? Show that the numbers 6k plus 5 and 5k plus 4 are relatively prime for any k into z. Why? If k equals 0, you get 11, 9 relatively prime. If k equals 5, you get 35, 24, 35, 24 relatively prime, and so on. For any value of k, those two numbers are relatively prime. You need to prove that one. You can see, right, if you try to use the general definition of GCD, it is difficult to prove that one, right? But using that earlier theorem, AB relatively prime, if and only if there exists xy such that ax plus by is equal to 1. So if you find some xy such that which satisfy that, that means GCDAB equal to 1. So you can try that way. So you can see 5, 6k plus 5 plus minus 6, 5k plus 4 is equal to 1. Because 30k cancel, 25 and minus 24, it is equal to 1. Therefore, that theorem, GCD 6k plus 5, 5k plus 4 equal 1 for all k in integers. Okay. So that is the today's lesson. I just want to correct some of the can you see my note now posted in the LMS? Let's see. It has some typos. Can you see my? I think you can see it now. Where is that typo? I noticed there dx by d. Yeah, there. So can you see this one? Oh, yeah. There. No. Yeah. Right. They are equal ARBS. It is trivial that, right? It is C equal ARBS. Right, C equal ARBS. Put C there, and also another one. Okay. And another typo, I noticed that CD, C. There, I mean, everywhere, it should be modulus A, right? I think it is something like that here. It must be modulus A. And the space must be here. And oh yeah, that are the typos. Be careful about typos, right? So that are the typos I found. Perhaps you can find many, but however, I think you can understand the proof. You know, I show you. So these are some activities, of course. Perhaps, yeah, this is a good application of. So I want to mention you that you know already how to prove root 2 is irrational, right? But if you try to prove root 3 is irrational, you cannot use the same method, right? So I can give hint to prove that you need Euclid lemma actually. Actually, from Euclid lemma, you can show that this one, this I can a sublemma. What is that? If P is prime and P divides AB, then P divide AO, P divide B. This is direct application of Euclid lemma. Of Euclid lemma. Try to prove. Right? A direct application of Euclid lemma. Try to prove that one. Right? Then to prove this kind of things, you need this lemma. Right? Okay. So we can stop today's lesson, and next session, I want to mention you about what we did so far. Lesson 1, actually in the lesson 1, we learned about n shade integers q, about this sets, learned about those sets, and in the lesson 2, we learned about basis representation right? And lesson 3, we learned about decimal expansion of we learned about decimal expansion. Lesson 4, well ordering principle. And lesson 5, divisibility. Lesson 6, division algorithm. Also the lesson 7, division algorithm. Now we learned about the greatest common divisor. And next week, we are going to learn about the Euclidean algorithm. It is again a very important algorithm. So from the Euclidean algorithm, you can find such x and y for any, this kind of x and y, GCD xy is equal to, AB equal to AX plus BY. Euclidean algorithm gave us a method to find such x and y, right? And also it has many applications. We will see it later. And the thing is, I couldn't give quizzes now because of this power cut, because only 1/3, I think 1/3 of all students come into the Zoom lectures. However, from next week, we want to find a method to give quizzes for grading. Perhaps I can find 2 time zones and I can give it separately. I will announce it to later. And also I will post a tutorial, but for the tutorial, again, it is for your self-study. It's not for the gradings, right? So that's it. So I'm going to end the session.